Welcome everyone. Welcome to Pushing the Grid to Edge webcast and turning the challenges of a changing energy landscape into business potential. This is brought to you by IoT World and sponsored by ABB in collaboration with ARC Advisory. I'm Lucian Fogoros. I'm the co-founder of IoT World, and I'm here together with Greg Orloff, our Chief Innovation Officer, who will moderate the session. And online, we have Carolina Rodiski, who will monitor the channels. So if you have questions, feel free to post them via Twitter using hashtag #IoTEnergy. So welcome, Greg.
Thank you, Lucian. Good afternoon and happy Halloween to everyone. So a little bit about IoT World. We're a digital media publication that covers the economic and technological implications of the transformation taking place as industrial IoT proliferates throughout the enterprise. IoT World combines journalistic coverage with data analysis to expose the stories, players, trends, and innovations that shape the IIoT. IoT World was recently ranked by K-Core Analytics as the #1 global influencer on several topics that include industrial IoT, smart manufacturing, ICS security, SCADA, predictive analytics, and predictive maintenance. IoT World's mission is to help companies create a culture of innovation and connect the smarts, industrial technology, manufacturing, sensors, and the CXO decision makers of the world. Today we have an exciting panel representing companies such as ABB and ARC Advisory Group. This webcast is designed to be a virtual 90-minute conference on the topic of distributed generation technologies. So in this webinar, you're going to learn what distributed generation and what grid edge means in practical terms, trending applications, challenges, and barriers in market outlook and growth. Also, our speakers will explain how to turn the disruptive effects of distributed generation into a profitable business model. And we're welcoming your questions, as Lucian mentioned earlier, on Twitter, and we can leverage the hashtag IIoTEnergy or the chat option that we have here on the platform. So our first speaker, his presentation is State of the Market. And Harry Forbes is the Research Director of Automation for ARC Advisory Group. And he's going to touch on what distributed generation and grid energy or grid edge mean in practical terms. What are some of the trending applications and new projects that they've seen? Some of the challenges and barriers as well, the market outlook and growth. So a little bit about Harry before we bring him online. Harry is ARC's lead analyst for the distributed control system DCS market. In addition, ARC leverages Harry's utility expertise in its coverage of smart grid, industrial networking and communication standards, and the electrical power vertical industry. His research topics include the DCS integration and architecture, smart grid, smart metering, energy storage, industrial wireless, industrial Ethernet, and emerging network technologies. Harry has over 30 years of experience in automation, power generation, energy management, modeling and simulation, advanced control, and optimization. And he has written for Control Design, Power Magazine, and Hydrocarbon Processing Magazine, as well as for many technical and industry conferences. Prior to joining ARC, Harry served in a variety of marketing, sales, and engineering posts for Simsky Escor, Inventus, and Foxborough. He also worked as a performance and automation engineer in fossil and nuclear power generation at Detroit Edison Company. So Harry, the floor is yours.
Thank you very much, Greg. The increasing penetration of distributed energy resources, specifically solar photovoltaic and wind and other distributed renewable electric generation, is changing the way the grid operates today, and we can see it in all kinds of markets. We can also see it's changing consumption patterns, and this is requiring new and more advanced grid controls and pricing models and business models. So what I'd like to do is go through some of the research that we've seen in ARC and also in the global markets to illustrate some of these behaviors. So first, let's look at what this means in practical terms. We've seen a big slump in the market globally for large. and this has been in the news lately, but the slump has been going on for several years. Here are two charts. On the left, new coal-fired generation capacity, with the Chinese market colored in blue and the rest of the world in red. China is a bit of a wild card going forward in this market, but you can see clearly the trend is down. And besides the downward trend in new capacity, older units are also being retired at a rapid rate in some market segments. The second chart on the right shows new gas turbine generation capacity. And this has been in the news quite a bit in terms of problems that major suppliers of new gas turbine capacity have had in the business in the last year or two, specifically General Electric and Siemens, but that's very much had been in the news. Suppliers of gas turbines were predicting much larger market and had designed new models to address this market, but utility uptake has not been anywhere near what was expected just a few years ago. Now we look at the reasons for this, and we can see that it comes down to an uptake in renewable technologies. Renewable markets have been growing rapidly. And here are two more charts showing the other side of the coin. These charts represent solar photovoltaic markets. The one on the left shows the growth of annual installed capacity. And the one on the right shows the split in that capacity between utility scale solar PV and rooftop or kind of commercial residential segments. So what we see clearly, even looking globally at the markets, is a big change between the type of generation that is being acquired and the type of generation assets that are being put online in the grid. Now, if we look at how this changes the properties of the grid, what this means is that the electric grids in every region are in a period of transition, and here are just a few of the major changes. And different regions will be at different points in this transition, but this transition is going to go on for a number of years. But the impact is that we're trending to much smaller units. We're trending to many, many more, or even tens of thousands of generation assets owned by not just utilities, but by independent power producers and commercial entities and residential entities. And the power flow is going to be multi-directional. If we look at what's going on in terms of new applications and new projects, ARC has done some fundamental market research, some primary market research in this area. And we have done a couple of studies on what we call microgrid automation. And a microgrid is a bit of a slippery term, so let me define what the term means to us. A microgrid is really a group of interconnected loads and distributed energy resources that operate within a clearly defined boundary and that can act as a single controllable entity. So this can be a number of different kinds of structures, but basically it's a distributed energy resource which can operate as an entity. In our research of this phenomenon, ARC determined that there are really three primary elements of control for microgrids. These being the primary control, which takes care of equipment protection, safety, and so forth. Secondary control, which is what is managing the load and controlling all the distributed energy resources. And the third, or tertiary control, is essentially remote control, remote connection to the grid, and control and optimization based on price signals and forecasting and so on. So this, in a way, mirrors the kind of controls that occur on the grid, but at a smaller level. So one element that the grids needed for sure was control, the second element that microgrids or distributed energy resources need is storage. And this chart is a bit of an eye chart. You can look at it later. But what we are showing is two log scales. On the right, on the horizontal axis, is the storage capacity in megawatt hours. And that you can think of in liquid terms as gallons of water. And on the vertical scale is the delivery capacity in watts. So that's like gallons per minute. So flow and volume if you're mechanically or hydraulically oriented. And into that we have mapped the different kinds of storage technologies which can take place in very short time spans for applications like frequency control and very longer time spans for load shifting from peak to off-peak situations. And what we find is that at the present market is really dominated by lithium-ion batteries. So if we look at the challenges and barriers to this market, what we see is for distributed energy resources and microgrids, the key drivers are government regulations and wholesale market access that enable broader participation in energy markets. The need for reliability is another driver, as outages have proven that distributed resources can be valuable, and there are many critical assets that require these kinds of extremely high reliability supplies. Also, growth of power in developing economies in areas not served by the grid, and the need to integrate distributed energy resources. And we see new solutions emerging on the market in terms of grid, microgrid, or distributed energy resources as a container. There are also inhibitors to the market, these being, again, I would say legacy government regulations, which are the old monopoly utility model, which we will still find in places, and subsidies for different forms of energy, and tariffs on equipment like solar PV panels represent a threat to this market. The second major problem is really a lack of expertise in terms of developing a business case, technical and design know-how, and the rapid evolution of the market, which I'll get to in a few slides. For the storage area, what we're finding is that we have the same sort of drivers in terms of government regulations, where access to markets creates opportunities for these technologies to return value to investors. And the increased penetration of non-dispatchable generation requires grid stabilization. In terms of the kind of inhibitors that we see in the market, one risk factor is the market for lithium batteries, which, as I said, dominates the market right now, but is also used in the electric vehicle market. And while this capacity is of this kind of battery technologies is a little bit uncertain at this point in time, given the uncertainty in the demand for EVs and the uncertainty with which this new capacity for manufacturing batteries will be developed. Again, regulations, monopolistic style, legacy style regulations are a problem, tariffs are a problem, and subsidies for other forms of energy. And again, the low cost of fossil fuels in some markets, particularly the low cost of natural gas historically in the North American market. So our strategies for success for end users in these markets are, first of all, to learn the regulatory and interconnection policies of the local market in which you operate. Second, to carefully determine the functional requirements of your distributed energy resources and assets. Understand the way your assets need to behave and operate and be maintained on all three of those control levels that I spoke about. And work with consultancies and with your suppliers based on these requirements that you've already understood. Finally, you have to manage the capabilities and scalability and the total cost of ownership of your microgrid. And you also have to be aware that as these types of assets take over a larger and larger portion of the generation capacity that's in use, cybersecurity will become an increasingly important part. So take that seriously at the get-go. On the storage area, understanding of local regulations and requirements is also important, but there are also opportunities for evaluating different kinds of financing options and ownership options depending upon the type of business and the region in which you're operating. People need to understand the levelized cost of storage, which requires life cycle estimates and modeling of the behavior of the asset. Again, there are plug-and-play packages that can enable people to include storage in their asset base on a more or less plug-and-play basis, complete with embedded automation. Finally, we'd say partner with experienced EPC firms, system integrators, and suppliers to ensure that you have a solid design and a solid implementation that enables you to expand flexibly. Let's look finally at some of the specific market growth that, as part of this market research. In terms of the grid scale battery market, we see the market growing at a remarkably fast pace of almost 40% compound annual growth rate for the next 5 years, which is about as far as our firm is comfortable making forecasts in this market. But the market is going to grow very rapidly at about a 40% rate to a market size in the billions of dollars. In terms of the microgrid automation component, which is what we've also researched, we see the market again growing not quite as rapidly, but at a 15.4% compound annual growth rate, again, into the multiple billions of dollars between now and 2022. So these are going to be markets that are going to grow at significantly faster rates than we will see in the overall automation or in the overall grid equipment market. So there's certainly a lot of opportunity here. And what we see in terms of the embedded suppliers, or the leading suppliers, is a familiar cast of characters, if you will, familiar firms that already lead the markets in other areas of electrical and grid equipment. But notice that the market is considerably unconsolidated. It's not dominated by a few firms, but there's a lot of other in the market. Even the firms with the largest shares are not dominating the market. So it is a more widely distributed, unconsolidated market in comparison to the more mature markets that we see in other types of grid equipment. Let me summarize what we find from our research in terms of the impact on the owner-operators of distributed energy resources. What they really need to have is understanding of the regulatory environment in the regions in which they're going to be operating their assets. They need to understand the life cycle cost of the assets that they choose to deploy. And they need to understand that in some detail. They need to enable themselves to scale easily so that as opportunities change and regulations may relax, they can grow without, and do that at a favorable cost point. And from a technological standpoint, what they really need to make sure they include in their resources are the capacity for energy storage and the capacity to automate or control those resources. That wraps it up, Greg.
Thank you so much, Harry, for sharing that with incredible insight with us. So as we transfer control to our next speaker, the presentation is entitled Integrating It into the Larger Energy Ecosystem, and we're talking about the grid edge. Our next speaker is Johan Kreusel. He is the Senior Vice President of ABB. And he's going to walk us through what are the key requirements for a proper integration of decentralized energy resources into the changing power systems. From a digital perspective, he's also going to touch on one of the key elements of a digital ecosystem for the energy sector and how we can accelerate this integration. So a little bit about Johan. Johan Krusel is the Senior Vice President of the ABB Group in Zurich and Marketing Innovation Manager for the group's Power Grid division. He studied electrical engineering at RWTH in Aachen University, Germany, where he was also granted his doctorate. In 1994, he joined ABB, where he held managing positions in marketing and technology. And before his current position, he was heading ABB's Smart Grid Sector Initiative from 2011 to 2016. Johan has been chairman of the Power Engineering Society, ETG, within the German Association for Electrical, Electronic, and Information Technologies, VDE, from 2008 to 2013. And he is vice president and member of the executive committee of T&D Europe and member of several committees of the European Commission and the German government on various aspects of the future developments of power systems. Moreover, he is an honorary professor at RWTH Aachen University, where he teaches power economics and liberalized electricity markets. Johan, take it away, please.
Welcome to everybody from my side as well. Thank you very much for attending this conference. Maybe a few words as an introduction to ABB. For those that shouldn't know us, we are a globally leading provider of solutions for industrial automation and power grids, and we're quite old, or our predecessors are quite old, more than 125 years, and you may say we are one of those companies that originally invented electricity, and we still have a certain mission to do that again in this transition. That is why we also do some very fundamental work, which is naturally pretty much technical oriented. So I hope it will be nicely complementary to what we have heard before. You may say we are engineers with a long tradition to get things done, and we hope we can do that again. Having said that, a few words as an introduction on challenges that our customers working in the area of electricity supply are facing. And this is, there are a few of them which are around resulting in a certain threat to reliability of supply. There are a few new ones, as we have heard before. There is renewables penetration, and we will see very soon what that means in practice. There is a need for improved customer engagement coming both from expectations from, let me say, normal customers consuming electricity, but maybe even more challenging from those that do not only consume electricity, but also generate electricity, being part of this distributed ecosystem that we have heard about quite a lot already before. Is this all about the future, or does it happen already? Well, surely the answer to this question is not the same everywhere in the world, but I would like to highlight a few places, particularly one in the world where you can see what it really means. And this one is a relatively small country, it's Denmark, and Denmark started the transition very early. So they took action immediately after the Chernobyl nuclear power plant incident in '86, developed a quite progressive strategy on transforming their electricity system, which at that time was primarily defined by a few big power plants, which you see on the left side, and they started this journey very early. And on the right side, you see how it looks today. Nearly no big plants anymore, but a lot of much smaller ones, and I would argue that is even not the full picture because you don't see rooftop solar installations there, and I'm pretty sure that there are some in Denmark in the meantime as well. The other example without a slide, just giving you a number of figures, is Germany, the country I'm living in, which because of its particular feed-in tariff structure became a pioneer in rooftop solar installations. And in the meantime, we have about 45 gigawatt installed capacity in solar power in Germany, a country with a peak load of 80 gigawatts. So you may imagine what that means, more than half of peak load installed in variable solar capacity, and by the way, another 45 in variable wind solar capacity. But these 45 gigawatt solar capacity are distributed among 1.6 million installations. So we're talking about millions of active elements of, you may call them generators, 45 gigawatts obviously is generation capacity. Millions of them instead of around 1,000, which we used to run the system with in the past. And I would like to mention also that just 1 or 2 days ago, for the first time in history, solar operators in Germany working in the competitive electricity market for the first time didn't get any subsidies anymore, because what they got from the market was higher than the subsidies than they are entitled to get, which means they have become a normal player in the market for the first time. And that is an important point to understand how this journey will continue. These technologies have become competitive. These technologies, particularly rooftop solar, PV and batteries, are highly modular, very scalable, so they can be installed easily by even small private investors, which means we have a completely different investment dynamics than we were used to have in power systems, which normally were thoroughly top-down planned, with a certain coordination between generation investments and network investments. Well, that's all past. As I said before, in ABB we are thinking about how this world may evolve. On one side you may say because we have a certain tradition in that from the past, but on the other side of course also because we would like to know how our markets will look like, what solutions will be needed in future. And we call this activity Power Systems of the Future, which is a work stream within my responsibility. And very briefly summarizing our view of this world is we're coming from a well-structured, top-down planned world with a hierarchical structure of the industry as well as technology. Load flows usually had a clear direction from bulk generation through transmission and distribution networks, which were named like that because of the clear direction. I guess today you wouldn't call a distribution network a distribution network anymore, because it's both distributing and collecting to consumers. In the meantime, today we say we are somewhere in a transitionary phase. We see already this high level of distributedness or fragmentation occur. We see a significantly increasing complexity. We see first moves into at least some more autonomy or separated systems, and we will hear about an example of that in the next presentation from my colleague Sliman Saliba. But the environment is still, you still see the roots where it's coming from. And at the end of the journey, we foresee a much more complex system with much more complexity on the grid edge, on the distributed end, with millions of active elements that need to be coordinated. We are very sure that this will not be done as it was done in the past, primarily controlled by humans. So machines, software, artificial intelligence will definitely play a bigger role there. Autonomous or partly autonomous solutions will gain relevance. So this is the grid edge and the distributed part, but you may be surprised that at the same time we have a global network there, which is maybe the most extreme vision. But what we want to indicate here is that we surely see a driver for larger interconnected systems than we used to have. And the very simple reason here is the variability of the new renewables, which if you look at one of the ways to deal with that is to get bigger samples, mathematically spoken, to benefit from complementary weather and demand profiles and to get a balancing. And we see the benefits of this already within the existing interconnected power systems, but we also see benefits of going beyond that. This, of course, is a very long-term vision. It requires not only technology. I would say technology is the least critical path toward this future. It requires political cooperation, business models, cooperation among companies, but it is definitely an option to deal with the variability brought by the new renewables. It's not the only option, but it's a viable one. So what will characterize future power systems? I don't want to go through all of the entries in this slide having quite a lot of text. You will get them afterwards and may read this summary, but I would like to highlight again the biggest driver for change for sure is the fact that we are talking about millions of legally independent actors that are still connected to one technical system. Liberalization and unbundling 20 years ago already brought a separation between companies, an unbundling of companies, while still being connected to one, you may say, production system, which has to be technically coordinated. And those of us who have worked in this area know that that was not easy going to translate all the technical requirements into market rules that ensured stable operation and also reasonable reinvestments. I would argue there are still a few gaps, hundreds of thousands of legally independent players. We're talking about millions and many of them non-professionals, and that was addressed already before. So this will require another way to deal with it. It will require other concepts to connect all of them. And when I'm talking about connecting here, then I'm talking about digital connecting. And of course, there are approaches which we have already today. There are a lot of building blocks that will help us, but there are also open questions. So for instance, in the right-hand column under new concepts, you find an entry called peer-to-peer approaches. So that is one of the things people are quite excited about. New technologies like blockchain technologies are mentioned here. So this is surely an open question to what extent this will also help solving the challenges. So there are open questions, but there are also a lot of building blocks available already today, but not yet deployed to the extent they could be. I will skip this slide in order to save some time for the following ones. I hope it became clear so far that digitalization of this future world is not only an option, it is an more or less inevitable necessity, and we are happy, we are lucky, you may say, that we have all the possibilities of digitalization that are available today in order to manage this transition. So it's a necessity, but it's not necessarily easygoing. I mentioned already, so a few challenges here, which we need to deal with, and it starts already with the one I discussed before. Deregulation, liberalization, unbundling has resulted in multitude of roles and responsibilities, and I'm very sure that we will see more new roles, new players, reflecting the technical changes that we have seen. But that means we have an ecosystem in which has to be open for new ideas. What we also see is, and that is mentioned down here in the regulatory environment, regulation, the legal framework of power systems, of power markets, electricity markets, is setting the framework that should ensure that all the legal actors independently optimizing their business in the end should provide all the services which are required to maintain the technical system, to keep it operational, to ensure affordable and reliable provision. Technologies are subject to change. The regulatory framework, of course, needs to be developed further as well. But no one has ever built such a technical system, so somehow this is a moving target. It's simultaneous engineering, and to make a long story short, it means we will see a lot of changes in the regulatory framework. We have seen them already in the past, and that will not stop. This will continue. Of course, this makes things much more difficult. If you integrate players, if you have to coordinate all of them, and then you have to expect that the framework will change from one to the other day, this may be a reasonably big obstacle. And let me jump to the next slide at that point, because part of our conceptual answer to that is what we call the Internet of Energy ecosystem. What it is about, we have on the left side in this slide, and in the left part of this slide, we see what we call the assets, so all the physical equipment out there, generation assets, the grids, of course, but also all the installations on consumption side, on either industrial or commercial or residential sites. We have also added, as an example, e-mobility here and storage. So these are all the assets that need to be technically coordinated. On the right side, we see the players, which have different business models, being generators, aggregators, may also be, I don't know why we forgot them here, the prosumers. Grid operations plays an important role, of course, market operations, and retailers. The challenge is now in an unbundled market, the connections between the assets and the players, and also among the players themselves, may always change over time. The functions they would like to execute should develop over time as a matter of normal business innovation, and regulation as the framework will also change. So one of the challenges we are facing is that IT systems and OT systems, making all that happen, contain on one side a more automation related part, a base functionality, I would say, to coordinate things, which is pretty much standardized all over the world, because it's basically implementing the natural laws. And then we have what we call the applications on top of that, which are reflecting business knowledge, regulatory framework, which are company-specific, country-specific, and permanently evolving. Traditionally, all these things were pretty much linked in OT systems, and change was not so easy. What we see now, and what we are doing in our company, of course, is a decoupling of these base functionalities and the apps that you can connect to them, so that you become, this is why we call it the Internet of Energy ecosystem. And you see under the key elements, the building blocks, the ingredients that enable us to do so. So it's cloud technologies, it's of course communication technologies allowing us to connect all these things, and at the same time decouple functionalities. It's analytics coming not necessarily from our domain, but from other industries. So the degree of flexibility has dramatically increased. So that is for sure part of the solution for the challenges, and part of the support of making the transition happen. Just to, of course, we have to a little bit to refer to what we have already in ABB. So in ABB we call this digital strategy, and not only strategy, it's our solution portfolio, ABB Ability. I'm sure you've heard about it before, if not then now. And just to make you aware on which experience we can build, ABB has all over the world installed about 70,000 supervisory systems connecting 70 million of devices. So that's quite a big experience on one side. It's also quite a big infrastructure that we can work with together with our customers, of course, and create benefit for our customers. At the end of this presentation, I would now like to have a closer look at one example, and that is, I have to say, more grid related, and the very simple reason for that is that in the following presentation from Sliman Saliba, he will talk about the part, you may say, beyond the meter or more on the grid edge. But you will also see that what I'm showing here on the example of a grid operator is also useful for actors operating a lot of distributed resources, which not necessarily need to be part of the grid. The examples that I would like to talk about is the integrated service and maintenance concept, which we have implemented in our Ellipse solution. And the three main modules we are talking about here is investment planning, it's workforce management, and it's enterprise asset management. And the beauty that the particular benefit that we could bring in here is that on one side we have our digital strategy, we have our digital solution, but on the other side we have, of course, also very detailed insight in the performance models for all the assets we are talking about, because we are an expert in building in transformers, in breakers, and all the equipment which is connected to the grid. So it's a quite unique combination out of digital expertise and primary equipment expertise. As we will hopefully see soon, there it is American Electric Power, the largest transmission network operator in the United States. You see the figures, so they own quite a lot of assets, quite an extended network with more than 250,000 miles of lines, distribution lines, and then another 40,000 miles of transmission lines, serving more than 5 million customers are connected to their grid. And what we did here is we implemented this asset management suite of applications in their network, and of course we also tried to find out the benefit together with them, and you see here the results of an external consultancy who validated the value of the lifecycle management, asset lifecycle management at American Electric Power, provided by the solution we have jointly built. So there are remarkable saving figures. You see them always in the million range, coming from reduction of significant failures because of proactive identification of issues within the asset so that you could take action before the failure happens, but on the other side are not forced to have a scheduled regular maintenance without knowing the state of the asset, which is the traditional approach. If something was important, you would have maintained it regularly without knowing whether this is necessary, which on one side is costly, and the other side also creates an implicit risk for the infrastructure, because whenever you touch it, there is a risk that something goes wrong. So it's costly and not necessarily supporting reliability of supply. Whereas if you get the right information and only work where it's necessary, you have various contributions to better business situation. I think we do not need to go through all the examples case by case. If you have particular questions, I will be happy to answer them in the Q&A session, and that brings me to the end of the presentation. Summarizing, the energy sector is experiencing a tremendous transformation, and I would say I've called this transformation in previous presentations. It's about inventing electricity a second time. It is really not less than at least inventing the way how we operate systems, how we manage them a second time. Of course, transformers are still transformers and circuit breakers are still circuit breakers, but the way how we operate the system, it's turning systems somehow upside down. And we can be happy that digital technologies are available that are the one opportunity to make that happen, to benefit from all the advantages that these distributed resources are offering. The price we have to pay is an increased complexity of energy systems. The other part is speed of change is faster than we have ever seen before and less predictable than what we have ever seen before. If you look at the last decades, it's fair to say that there were no real breakthroughs in technologies defining the electricity systems. But if you see what has happened, for instance, with solar PV from 2009 to today, the dramatic cost reductions, it's fair to say that this is a dramatic technological change. So it's a completely new situation, and somehow the same applies, not that dramatic, but dramatic enough with wind power and with batteries. So the ingredients of the system for the first time since a very long time are significantly changing and much faster and less predictable than we were used to. That requires more flexible approaches, more adaptive approaches. The traditional approach of thorough planning and not starting to deploy anything before you have understood it perfectly well is not applicable in this environment. So we have to become more adaptive. We have to think about concept strategies which allow us to correct things faster and with less impact than in the past. And the Internet of Energy ecosystem is at the core of that allows us to respond faster to changes that we have not foreseen. Well, and last line, a little bit of sales pitch for ABB. We have also transformed our organization. We have introduced a digital organization at the core of the company, at the core of its strategy to reflect this opportunity. And we believe we have a quite unique combination of digital experience and knowledge with also knowledge on all the physical assets out there in the area of electricity. So I think we are reasonably well prepared for this transformation. And we are very happy to share that with our customers and other members of the ecosystem, of our ecosystem. So that was my introductory presentation, and I'm curious about the questions that we will get after the next presentation. Thank you very much.
Thank you very much, Johan. That's some excellent insight. We're going to now turn our attention to actually turning disruption into opportunity with control and optimization. And Sleiman Saliba, who's the product manager of energy optimization, BU power generation, and water for ABB, is going to walk us through his presentation, plants and energy management. He's also going to discuss how to turn the disruptive effects of distributed generation into a profitable business model, and how to maximize revenue while you're going green. Sleiman is responsible for the global market introduction of energy optimization solutions for virtual power plants, industrial and commercials, as well as smart cities. This way he brings together his passions, his protecting our climate for future generations and making ABB the market leader in green energy. He believes that the integration of renewable power is essential for ensuring sustainable power generation into the 21st century. He's passionate about developing new technologies and bringing them into the market. Sleiman, the floor is yours.
Thank you for the introduction. So I will talk today about 3 companies in very different areas who use changes in the energy environment to increase their values. So as Jochen introduced in the presentation before, the energy and grid transformation is driving changes in how electricity is generated, transported, and consumed. And now, what we see at the moment, this new grid, it's about a bidirectional energy and information flow. The global turn towards renewable and distributed power generation that's disrupting our landscape. So what we see is that smaller and more decentralized power generation units are dominating the market. And so the result is that we are living in a complex environment and generation is shifting. So before we had a traditional grid with bulk, centrally controlled power plants, and now we have distributed, decentralized, weather-dependent, volatile sources. And so what we are facing now is the challenge to control and optimize these new systems in a reliable and profitable way. And when I say reliable and profitably, this change presents an opportunity to leverage the benefit of digitalization, and we can actually use changes in the energy market to get new opportunities. So when we look at different industry segments, for example, industrial and commercial site owners, their need is to cut the energy costs and emissions. And they are required to comply with legal or corporate requirements in order to reduce the energy cost and emissions. And in order to do so, they need to be able to control the power and the emission. And that's often the first obstacle. So systems that are able to measure, monitor, and control energy are often not in place. So what they face is that they spend a huge amount of time to create reports on energy consumption and on energy reduction. The other industry segment, for example, utilities or vertically integrated utilities or city municipalities, their driver to change is that they have the need to better control, monitor, and optimize their grid-connected assets. And that's in order to manage the bidirectional energy and information flow. And this all why the energy demand is increasing in their region or in their portfolio or in their city, and also the renewable generation is increasing, which is volatile and let's say predictable, but not as predictable as we were used to in the past. And often the control systems that are in place are not able to do this frequent and fast pre-planning of the generation schedules. When we look at energy suppliers or power providers, their driver is that the traditional revenue flows are drying out. So the bidirectional energy information flow, innovative business models, and the legal requirements are changing that are allowing this changing business models. And that can be both-sided. On the one hand, new players are emerging, which are driving the cost reduction part, and the traditional revenues are drying out. On the other hand, energy providers and energy suppliers can use that to also change their business models and also offer new services to their customers. So these companies from different segments have different approaches to the challenges that they have. So if we look at the industrial and commercial customers, so what they do in the first place is replace energy-hungry assets, okay? Then monitoring the energy use for each asset. This helps them to see where they have energy consumption, where they have peak loads, and they can adjust the operation to minimize peak loads or drivers for energy costs. Then you can go one step further and invest in on-site renewable generation and maybe also utilize storages on your site. But all in all, the last step to digitalization and to really leverage the value that you have is to install a software that can actually proactively manage the controllable loads and the on-site generation and the grid connection in such a way that you operate your assets and your industrial and or commercial site in the most cost-effective way. For utilities or vertically integrated utilities or city municipalities, we just saw in the last slide that the disruption that they face stem from the shift to bidirectional energy and information flow. And often the applied control systems, they are not sufficient to cover these new requirements. So what they need is a control and optimization to make fast automated decisions in planning, replanning, and executing schedules for the controllable assets. And this all, of course, in the most economic way. And finally, energy suppliers and energy providers, they are moving from the traditional and by now not very lucrative simple energy provision to more an aggregator role. So this means that they are not only operating their own assets, but they actively seeking other assets to contract them and to increase their basis for energy supply. And moreover, they're also actively looking for partners to develop additional services to their customers, all that beyond the simple energy provision. And therefore, we call that they offer their customers energy as a service. So it's not only about getting the energy to their customers or providing them with energy, but really providing them with additional services to increase the margin for the energy supplier and to keep the customers, of course. So just to recapitulate, we're looking at three different segments: independent power providers, where they have where they integrate decentralized generation assets into a large-scale virtual power plant. We have industrial and commercial site owners who face the pressure to reduce cost and increase their revenues. And we have a city municipality as reference use case where we show the optimal operation of decentralized energy resources in a so-called smart city. So when we look at the virtual power plants, that's one of the solutions for implementing a business model shift. You can aggregate and integrate this decentralized generation, flexible load, and storage systems. And the task is, and the goal is to enable cost-effective participation in energy market and cost-effective operation of the assets or the technical units in your portfolio. So you control and optimize from a central control system and create a virtual power plant. And in this way, you can combine very dispersed, decentralized energy resources from multiple sources into one optimized entity. And with that, you can plan and adjust the production dynamically, and you use forecasting to do so. And if this is applicable to your market, having this higher insight into your portfolio with the forecasting, with the planning, and the capability to replan really, really fast and often, you can use this flexibility and the new insight into your portfolio to trade on energy markets. And with this architecture that you get, you can also implement your business model. And this probably is depending on the country where you're living in or the region and the type of assets that you have in your portfolio. And finally, you can really make use of coupling many sectors, especially in cities. That's interesting if you have electricity, gas, heating, cooling, water, and e-mobility in your portfolio, or you need to manage them together. You can really cross-optimize between these sectors. And that's how the control system looks like. I'll not go into details, but in the end, it's about day ahead planning, then replanning during the day, and the real-time execution when it comes to the commitment. And here we have a use case of Next Kraftwerke. That's one of the largest virtual power plant operators in Europe, and they really used the liberalization of the energy market in Germany to create a completely new business model. So they started 2011 with a pool of 20 biogas plants offering capacity to the ancillary market. Within the first 3 years, they grow from 20 units to 2,800 units. And all these new customers were added continuously without any interruption to the operation, because all the hardware and software additions were made without a system shutdown. And by now, so 8 years later, 7 years later, there are more than 5,400 units integrated in 8 countries with 4.5 gigawatt of installed capacity. So when we look at other use cases or other industry segments, especially in industry or commercials, we have industrial sites that install on-site generation or already have on-site generation, and by optimizing the usage of the generation assets, of the storages, of the grid connection, and the controllable loads, they can save an additional 5 to 10% on energy costs. And the interesting example here is that it's not only about the big, heavy process industries like cement, metals, and pulp and paper, it's really, you can scale that down to small and medium-sized companies or sites. As an example, we did that for Smart Farm in Germany, and really the self-consumption was increased from 31 to 50%, and the grid purchase was reduced by a quarter, and the peak demand was reduced by 10%. So in the end, the benefit here is not only to decrease the cost, but also to really save the time on reporting. Because in the end, you have one source of energy data where you can take all the data out and make the reports that you need. Yeah, and here we see the table again for the Smart Farm. So that was over the test period of 1 month. So the peak load was reduced by 50%. That's probably a very special case here. So you can't expect every site to reduce it by more realistic. But in the end, you see that the grid purchase can be reduced significantly, and the self-consumption rate of on-site generated energy is increased. And see the system architecture, control system for industrial and commercials. And you see it's a very modular system where you have the forecasting, the optimization, and the visualization really bundled into modules that are available today. Then the final use case is about smart cities. So when we talk about smart cities, it's we often talk about smart buildings, smart automation of factories, monitoring of power and water distribution and district heating networks, of installing EV infrastructure, digital substations, or Wi-Fi on public squares. But that's all our foundation technologies. We need that in a city of the future. But however, the smart in the city really comes from integrating all these available technologies. The modern smart city demands the intelligent combination of these foundation technologies to really create sustainable solutions. And in the end, it's about having the information available faster and better so that we know more and generate more insights, and by that enabling a better decision making. And so we can reduce the time to react when it comes to emergency services, and especially we can decrease the operational cost when we integrate like power generation with the power network, the water network, the heat networks, and controllable loads. And in the end, it's to make municipalities more attractive for its citizens, because in the end, cities are competing for companies, for trade, for citizens, and increase the daily life operation. So, and we also have an example for that. It's Västerås in Sweden, where we partnered with Mälar Energy to have an integrated control room where these many automation systems are brought together to create a unified operating environment. And these assets that we bring together, these automation systems, that includes the power generation system, the district heating system, power and water networks, and the fiber optic communication network. Actually, it contains a bit more, like all the emergency services are bundled in this control room. But in the end, it's about and support the operation. It's about analytics and about predictive maintenance. And all in all, what we can benefit from that is that we optimize the asset performance, and provide integrated infrastructure services to Meta Energy. And yeah, the goal is to have a city operation that is more efficient, more sustainable, and in case of emergencies, more resilient. And all in all, make it a more attractive place for citizens and industry to live there. So that's for me, and thanks to all the other speakers as well, and we are happy to take questions now.
Great, thank you very much, Slayman. So we are now going to move into the panel discussion and Q&A portion of our session today. So please, we've had multiple submittals come in, but if you still have questions that you're burning to have answered by the panel, you can either submit those here on the dialogue in the Q&A portion or the chat, as well as sending them into IIoT Energy via Twitter. So yeah, let me start with the first question here. We've seen the example of Denmark with a very high number of small generation assets. Are there other examples where traditional ancillary services are provided by distributed resources already? I'll throw that out to the ABB team if someone would like to respond.
Well, it was Slayman's example, so maybe he wants to take it. Otherwise, I can say a little bit about it.
Yeah, so it depends on which kind of renewable sources you're talking about. Like we see first installation of wind that are pre-qualified for tertiary reserve. Solar is not yet on its own pre-qualified, but together with battery storage systems, you can use them for ancillary service calls.
Maybe as a broader explanation, so the next Kraftwerke, this example from Germany, was originally funded when the framework, the legal framework, or no, it is not the legal framework, it were the grid codes defined by the local transmission system operators were changed in a way that, first of all, the smallest entity entitled to participate in a control power market was then 1 megawatt, before it was 50, and pools were accepted. So that immediately resulted in Next Kraftwerke offering secondary, they offer primary, secondary, and tertiary reserve based on their distributed assets. So far, this is offered based on biomass, which is basically gas motors. It's renewable, but it's not wind or solar, but that is not because it would not be possible, it is because it's not yet allowed because of the grid codes. We are assuming that that will be changed. So there are discussions that all types of renewables will be entitled to participate in the control power markets. And not only in Germany, this discussion is going all over Europe. With solar, I would like to add just a nice example. If you look at the average size of a unit, an asset managed in the Next Kraftwerke pool, then you will see that this is a little bit below 1 megawatt, which of course compared to a bulk power station is reasonably small, but compared to rooftop solar is still a big one. And the very simple reason is that there is still not I would say, an IT connectivity standard allowing to communicate with such very small units efficiently. So this is an issue of standardization and in creating this digital ecosystem. We assume that there will be significant progress with the smart meter rollout, which is not only a meter rollout, but also a rollout of communication gateways for such assets. But that's the barrier at the moment. It's not regulatory or a technical problem, it's a business, it's an economic problem. So far all these distributed resources have to be connected more or less case by case manually. Somebody has to go there and install a proprietary box and connect that with the Next Kraftwerke dispatch center. And as soon as that will become public through an available communication infrastructure without having the need of sending somewhere there, then we assume that the average size of entities in the pool will decrease.
Excellent. Thank you both. Had a question come in from Mark Anderson. It says, very interesting presentations. Thank you to all. Well, thank you for attending, Mark. His question is, in an optimized portfolio, when balancing prosumers, how does an EaaS ensure equitable treatment of all prosumers?
There are many ways to answer that based on what you mean by equitable treatment of all prosumers. So let's start with the example that you contract assets that you take into your pool, and you get an ancillary service call. Then you want to treat all of them equally, or which means that you distribute the calls equally to all in your pool. You could also do that by using priorities, or based on the contracts that you have, or you can use the marginal cost, so that the cheaper ones are used first and the more expensive one last. Then there is the second aspect to when it comes to curtailment, when you want to meet the load demand, but suddenly you have too much energy in your portfolio or in your system, then you need to curtail generation units. And then it depends on the, again, on the legal and the contractual requirements. So sometimes legal requirements say that renewables are prioritized, so you need to turn down your fossil fuel power plants, which is probably the most expensive thing to do, because you turn them off and then you need to turn them on again. That's yeah.
Maybe I can add one thought. I think running such an aggregation business means having contracts on one side with a lot of the prosumers, and on the other side acting in the market. And I don't think that this necessarily implies that all of the prosumers are treated equally. It means that all of them need to have a bilateral contractual relationship with the aggregate, and but this does not necessarily need to be the same situation for all of them. Their capabilities may be different, and I think it's part of the business model of an aggregator to find all models to interact with them, that everybody gets his share, but not necessarily everybody the same, which means there is no simple answer. There's even no standard answer to the question. But I think it's important to understand that the business model is not necessarily bringing all of them to the market in the same way. It's just giving them some security, because the aggregator somehow filters the risk of the market, so makes life easier for the owners of the assets, but that has a price, of course.
Excellent. Thank you both. Quite a few of this repeat questions, so let me address a couple of these before we jump into another technical one. Yes, slides will be available after the session. You'll be issued access to those for the information, so rest assured you will get it. And several questions come in around certificates of attendance or accreditation certification. This is not, we're not offering that right now, but please put in the chat box if that would be something of interest to you for future presentations.
Yeah, I can respond to Kevin on that. We could actually issue a certificate on that. We haven't done in the past, but I appreciate us pushing for that, and we'll be happy to offer you one.
Excellent. Okay, I had a question come in from Hugh, and he says, why do utilities avoid time of use, since that helps to shift peak? Does anyone have a perspective on that?
I could say something on it. Again, not a simple answer there. I think that is, first of all, we have to be aware, I just want to say that first, that in a world with an increasing share of renewables, there may be conflicting objectives of time of use tariffs. In a traditional system where it was all about having assets, and the economically best situation was to have a constant loading of the assets, there was no conflict between the generation and the network part, because the best for all of them was a flat load. But in a world with volatile variable renewables, it's not the case anymore. The generation side may have a reason to artificially increase load to create peaks, because there is a peak on generation side at the moment, whereas the network operators will not like that. So that means that price signals, time of use price signals, become more difficult in general in this future world, and that conflict needs to be resolved. Behind that is an economical conflict. Then second, if you forget about that shortly, of course it strongly depends on the incentives an operator gets. For operators all over the world are capex based, or capex in favor of capex, of capital expenditures. So simply said, the more you invest, the more you get. Why should you try to break peaks in this case? It's against your business interest. And then there is another case that I'm aware of. For instance, I'm aware of that from some European countries. I'm not sure whether it's the same in the US. We were always thinking time of use tariffs would be a great opportunity to give to give signals to the consumers what they could do to improve efficiency of the overall system, and by that in the end of course get better prices. We were a little bit surprised when all of a sudden consumer organizations were opposing against that and lobbying against that, and their line of argumentation was, well, this is of course true in principle, but unfortunately these opportunities will only be taken by well-educated, wealthier people, whereas the poor and less educated people will pay the bill. So there are political initiatives against time of use tariffs, and for instance in Germany, time of use tariffs for the grid particularly, not for the energy part but for the grid part in the bill, are not allowed on residential level for this particular reason. So again, it's a pretty diverse answer, it's a diverse ecosystem, but I think you need to look into the particular case.
This is Harry Forbes. There's one other point I'd like to make on this, just to second that. From the regulatory policy standpoint, there's a lot of value in simplicity of regulation. So to make the regulations easily understandable, and especially in the residential consumer segment. And that's certainly one reason for it, whereas you can treat those kind of complexities much differently in the commercial and industrial sector.
Excellent. Well, thank you all for chiming in on that. Had a question that coming in for Harry. This is from Haji. This is, to what extent do you see government incentive programs playing a critical role in furthering the adoption of renewables?
I think they will, and again, this is kind of a region by region and country by country case, but the role will probably be less going forward than it has been, say, in the past, say 5 years ago. The cost of becoming competitive in all kinds of regions, save the ones where there are very low fossil fuel prices. So in more and more ways, there's less government incentive and less regulatory reform required to get these kind of assets deployed than there would have been 5 years ago.
Maybe I can add one thing. I fully agree. I think the need for active push and support of renewables is definitely decreasing. I would even say vanishing. It becomes more and more an economically driven process, but regulatory and legal frameworks, however, nevertheless need to reflect that. They can still block the progress. So if you have, normally renewables are, one strong driver are private investors. So if you have an integrated monopoly system where independent power producers have difficult or no access to the market, then this is definitely not in favor. But I think what is happening, the need for political attention and maybe action is shifting from subsidies to adapting the regulatory and legal framework to open the market and to relieve the power of economics.
And one other point I would make is that from a policy standpoint, if a utility is looking at providing service, the kind of metrics they have they don't have just one metric. They have a metric of providing economical service, but also providing reliable service. So there are multiple metrics applicable to the utility providers, and that enters into these policies as well.
Excellent. Okay, here's another question that came in. It says, is talking about ABB's abilities, wouldn't using this platform mean to become dependent on one supplier only?
Well, no, I can take that maybe. No, not at all. We are, of course, aware that that would be a showstopper, basically. And so what we see is that such cloud-based platforms are increasingly also connected among themselves, so they are open to be connected among themselves. We are also not the only vendor offering cloud-based services, and well, of course, there may be some offering similar like us, and then we would, of course, encourage everyone to give preference to ours, but there are also others offering complementary services that we do not have in our portfolio. And then there is, of course, a must to connect. So no, not at all. It's more the opposite. These type of platforms allow to have standardized interface. It was not impossible, but it was much more difficult to maintain such open interfaces.
Great. I think we may have time for one more question. We've got one here. It says, in as much as nuclear power has taken a hot seat recently, do you envision a point in time when decentralized nuclear power generation could be integrated into a landscape? So I think they're referring to maybe small nuclear reactors.
Yeah, I remember that there had been such a idea decades ago. So my answer would be, is there anyone who is familiar with this? Maybe I'm not aware that this discussion has returned. So if
yeah, I'd be happy to.
Is more familiar, then I would be.
Let me just offer a comment on that. There have been several initiatives to shrink the size, the unit size of nuclear power with new technologies. The realization that the existing power generation technologies for nuclear power essentially haven't changed in a revolutionary way since the early 1960s. The value proposition there is that the unit sizes would be smaller. The units would be able to be constructed in a higher volume on a kind of a factory assembly line and distributed kind of the similar way to the way, say, gas turbine power plants are distributed now. What I would say is there's certainly some potential there. I would say it's very early stage, and the kind of participation that would be participating, the kind of entities that would be participating, I think would be both utilities and deep-pocketed private investors. So this would be larger scale operations than, say, what would be required to enter the wind market today at a utility scale. So it will be larger entities that will do it. And I would say it's still more than a few years off.
And just one question, and now I'm the other. I remember the one of the central ideas of this concept that I remember from the late 70s, I would say, which on one side, of course, was also targeting at this mass, well, mass is maybe a little bit too much, but at least a little bit mass production than the very tailored we're used to. So that was one pillar, one of the concept. The other one was that there was a new principle which was assumed to be implicitly safe, so that all the additional burdens for safety and security installations were expected to be decreased, which in the end didn't happen because legislators were not willing to trust in the implicit security. So is there anything which that means it drives fixed cost and means significant economies of scale per se, which result in a tendency to larger units. Is there anything like that around now?
There are such initiatives going on. Again, you need to find a receptive market for these and a receptive regulatory climate. So there is preliminary work going on within the United States on some of these, but I wouldn't say that there's necessarily utilities lined up and ready to deploy this technology at this point in time. That might be different in other parts of the world.
And just from to add on this question, what would be the advantage? That's more expensive, it's harder to control, and it's insecure. So compared to decentralized energy resources, when we talk about renewables, I don't see any driver except for using the small nuclear plants for other purposes than civil purposes to develop such mini nuclear power plants.
Yeah, without making a judgment on it, I would say that certainly the decreasing cost of renewables, and especially the life cycle cost decreasing, as well as the lower prices, commodity fuels like natural gas always impact this kind of technology because the capital cost is inevitably higher, and the bet is that the O&M costs over the life cycle can be lower.
Gotcha. Well, thank you all.
That is a questionable bet for sure at this point in time.
Controversial topic, absolutely. But it's always nice to see people weigh in with something that's outside the box. Well, that's going to conclude our panel discussion portion and also our presentation portion of the day. So I guess in closing comments, on behalf of IIoT World and all of our panelists, I wanted to thank everyone for joining us today. And stay tuned for some of our other educational webcasts that will be brought to you in the not too distant future at all. In the next several months, we've got several intriguing and interesting topics that are going to come out, and I'm going to turn it over to Lucian and let him talk to you a little bit about those.
Yeah, thank you, Greg, and thank you all, everyone, for joining from all over the globe and a multi-continent panel. Thank you, Harry, Johan, Sleiman, and Greg. As Greg mentioned, we have a number of videos that were uploaded on the YouTube channel from the Distributed Energy Conference, as well as on industrial or cybersecurity or securing the critical infrastructure, as well as we have some upcoming webcasts around predictive analytics and predictive maintenance and industrial cybersecurity for this type of industry, but also others. So with that, this concludes our program. Thank you so much.
Thank you too. It was a real pleasure and very interesting.
Yeah, thank you from my side as well. Bye.